So, pin assignment, that is what we want to talk about in this lecture. Let us try to understand what this problem really means. See, here we are trying to define the signal that each pin will receive. What does this mean? Let us take an example to illustrate. Let us say I have a block. This block consists of some kind of a gate level netlist. It can be anything. So, the exact circuit is not important. Let us say I have one output here, there can be another output coming like this, right. This is a circuit. So, as you can see, let us say these two are also combined. So, there are 4 inputs and 2 outputs. So, externally there will be a total of 6 pins, 2 input pins and 4 input pins and 2 output pins. Now, this input and output pins are not necessarily true that the input pins has to be placed on the left edge and the output pin on the right edge. Input pins, some of them can be placed on the top, bottom, or it may be possible that it may be good if I connect this one to this and this one to this, cross kind of a thing. Okay. There are lot of issues. These issues will depend on not only this block which we are considering, but also to the other blocks that are in the neighborhood, and from there the connections are coming. So, depending on the location of the other blocks, you will have to judiciously select where you have to put the pins. Now, this decision you have to take for the so called flexible blocks. Flexible blocks, you recall, are the blocks which are not yet been designed, their exact shapes and sizes are not fixed, and also the exact location of the pins are not fixed. Okay. For those blocks you have to take this decision. Now, this pin assignment can be done during various stages, during floor planning, during placement. I shall talk about this a little later. During placement also this problem can come up. Not only that, even after placement sometimes you may have to play around a little bit. This also I will discuss. Okay. This is something which we just now said. For blocks which are not yet designed, a good assignment of pins can improve not only the placement, but also the interconnection, the routing. But also for the blocks which are already designed, there is also some scope for pin assignment. Like, let us take another example. Suppose I have a block like this and I have another block like this. Let us say this block is just a 2 input gate. There are 2 inputs and 1 output. This is a fixed gate, and suppose there are 2 other blocks which are also fixed in their they are already placed. So, some circuit is generating this signal, some other circuit is generating this signal. Now, I have to connect this signal to this and I have to connect this signal to this. Now, you see here there is a cross in the interconnections. So, wherever there is a cross in the interconnections, laying out of this nets will be a little more difficult. It will take a little more space. Okay. This you can immediately see, because if 2 connections have to be made in parallel, it is easy, but if it is zigzag, then means one of them you can connect, but the other one there is a problem. You may have to go to another layer, then again connect like this, then like this. So, you may have to move to another layer, make a connection, and then you have to make the connection. It will take 3 tracks instead of 2 tracks here. Okay. It will also take more space. But what I mean to say is that, okay, suppose this is an AND gate, let us say. Now, since we know that the AND function is commutative, A and B and A are the same, so it really does not harm if we swap or exchange these pins, bring this here and bring this here, that will make the connection straight. The functionality does not change, the output does not change, it is simply the AND of these two functions, right. So, this is actually what I mean to say in this last point. So, in this pin assignment, the input is a placement of blocks, number of pins on each block, possibly an ordering. This ordering may or may not be there. This ordering means, well, you know that there are 3 inputs and 2 outputs, but you know that the order will be fixed, first input 1, input 2, input 3, then output 1, output 2, but the exact relative locations you can move them around, but their ordering has to be maintained. Okay. This may or may not be there as a constraint. Objective obviously will be to minimize the net length and also to see that minimum number of crossings are there. Functionally equivalent pins, 2 pins which carry the same signal, it does not matter if I exchange them. This equipotential pins, both are internally connected C and D. So, you see C, D are equipotential, A, B are functionally equivalent. So, the example I just now gave a little earlier, that is an example of a functionally equivalent set of pins. So, I can exchange A and B if required without changing the functionality. Similarly, C and D are electrically connected, I can also exchange C and D, so without any problem. Okay. So, if there is a scenario like this where C is connected somewhere, D is connected somewhere, if required I can exchange them. Well, if that means that my routing can be improved, my placement and my wires can be laid out in an easier way, I can do that. Okay. All right. So, the purpose is to optimize the assignment of nets within functionally equivalent or equipotential pin groups. Objective, as I said, to reduce congestion or reduce the number of crossovers. So, the example that I just now took, suppose this was such a case where these 2 pins, where you can see there is a cross in the interconnection, they represent functionally equivalent or equipotential pins. If such a cross is happening, you exchange them and make the connection like this. This looks much neater, much easier to interconnect. Okay. So, the blocks can also be brought closer together here, less area. Fine. So, here I shall not be going into the very details of the algorithm, I shall briefly give you the basic idea regarding the possible approaches that people use for the pin assignment problem. Okay. So, there are some general techniques which can be used for any general pin assignment instance, but some special techniques which can be used only for standard cell kind of design style, where you have the channels, the standard cell rows and so on. Okay. Let us see the concentric circle mapping. This I shall be illustrating with the help of an example. So, here let me tell you, here the problem is that I have a block. This is the problem of one particular block whose pins are flexible, but their ordering I am assuming is fixed. You cannot change the ordering, but you can rotate them if you want. There is this block whose pins have to be connected to some external points, some external other blocks which have already been placed, and I am assuming their pin locations have already been fixed. So, it is only the pin positions of this current block that you are trying to adjust at this phase. Okay. This is my problem which I am trying to illustrate. So, you see this is my block whose 6 pins, as you can see, whose ordering I can change, I can rotate their order. This pin I can bring here, this I can bring here, this I can bring here and so on. But this external these points which are shown as red, they have to be connected to these pins. Okay, they are already fixed, I cannot change this 6, right. So, let us see what this concentric circle mapping talks about. First step, it draws two imaginary circles, one inside this group of 6 pins and the other outside this group of 6 pins, but inside the external pins. So, you can see these two circles, concentric circles, right. These are imaginary circles we are drawing. Then from the center of the circle we draw lines, from the center of the circle we draw lines to the 6 pin. Let me go back once. Say from the center I draw a line to these 6 pins. Okay. These lines will be intersecting the inner circles at some points. Similarly, I draw lines to the external pins. Okay. They will be intersecting the outer circle at some points. So, that is shown in this diagram. The inner circle will be cut at these points which are shown, and the outer circle will be cut at these points that are shown, right. Now, we forget the original pin locations, we only consider these projections on these circles, the 6 points of the inner circle and the 6 points on the outer circle. Okay. Just we temporarily forget the actual pins. So, we take this. Then we do some kind of a rotation of the circle. How? Then we try to find out initial mapping first. Let us say initial mapping says this pin is connected to this pin must be connected to this pin, this is connected to this pin. So, the ordering is there. So, now you try to rotate them in some way. You see, this is a bad rotation. If you rotate this pin to here, then have to connect it using long wires. So, you try to rotate the pins in a way, rotate it in a way such that the interconnections become simpler. If you rotate in the wrong direction, then the wires will become very long. Okay. So, you find out the optimum angle of rotation for which your interconnection lengths, the total of them, is minimized. So, this can give you a good solution. Maybe you rotate it in the right a little bit, it will be even better, but this is a bad rotation. Okay. So, once you get the good rotation, this is the best rotation. So, you connect them in straight lines. So, now you know with respect to your chip, now you replace them by your external pins again. Your 6 pins were there. Now, on the concentric circles your positions have been fixed. Now, you connect the corresponding pins to the corresponding points. This will be your best mapping. So, if this means that by rotating the circle your original pin which was here has come here, you make it here, no problem, that will be better solution. So, just you allow the rotations, you make the best configuration, then again you come back to the original one, that how the pins were connected there. Then you see that where the pin locations are coming. So, from there you connect to the external points which are there, that will be your final pin positions. This is the basic idea behind the so called concentric circle pin assignment algorithm. Now, if it is to an external block instead of several external pins, so this slide actually shows you, illustrates you something on that. Suppose I am placing a block here, there is an external block for which the pins have already been assigned. Here for this block you consider the imaginary circle like this, but you take another straight line for which you take the projections from these points. Well, I am showing it like this, these will all be straight lines. Okay. So, So, for the projections, with respect to those projections, you find out the optimum angle of rotation of this inner circle. So, you compute the cost and then you find out the optimum angle of rotation. So, means roughly the idea I mentioned. So, from the external block you project them into a straight line by perpendicular, you can say, projections, and the block that you for which you do the pin assignment, you again use a concentric circle, make the rotations such that with respect to the straight line the total length is minimized, get the optimum angle of rotation, that will be your final pin position. Okay. So, this is how this method works. So, topological pin assignment is an alternate method which is quite similar to concentric circle mapping. In fact, it is a little easier. So, here you can just handle nets which is assigned to more than 2 pins. So, if it is like that, then the pin which is closest to the center of the primary component you take. Like what I mean to say is that, suppose there is a block where there are 2 pins, let us say one pin is here and means another pin is here, let us say here, and there is here a block where you want to do pin assignment, you have a connection here to make to both of them, you have a connection to both of them. You see, for this block, this is the center and this is the pin which is closer to the center and this is a little farther. So, you ignore this, you consider this, you forget this, you consider this. Okay. This is what is mentioned. So, the rest is quite similar. Okay. So, I am not going into detail of this. 9 zone method is somewhat a little different. So, here I am just giving you the basic idea. Here we are dividing the entire rectangular zone around a block into 9 zones. We name them 1, 2, 3, 4, these are the diagonals, 5, 6, 7, 8 are the 4 horizontal and vertical directions. So, whenever you have a connection to be made to an external pin, you consider them with respect to the center of this block. You see to which zone that connection belongs to. Like what I mean to say is that, let us say you have this block, you want to assign its pins. So, there can be many pins, okay, there can be many pins. So, what I say is that you consider the center of this block, and if you consider the external pins from where the connections have to be made, you look at them. So, from where these pins are coming from, and then you try to group them into zones. You can say that these 3 are falling into one zone, these 3 are falling into one zone, this is in 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 one zone, maybe there is another in this zone. So, you group these pins into zones and zone wise you assign the pins. Suppose the pins which are belonging to this zone, you take a projection, you assign them in this vicinity, these 3 pins you assign to these vicinity, these 2 pins you assign to these vicinity, these 3 pins you assign to this vicinity, something like this. Okay. So, this is a heuristic method which works pretty well. This is a zone based method where you define the zones and with respect to zones you do the assignment. Now, this channel pin assignment is a special method which is applicable to standard cell based design. So, this is one example I am trying to work it out and show you. So, what I am saying is that you can move some pins around. In this case, you can move the blocks around such that you can make it vertical, some of these lines. It saves space. How it saves space? Let us see. Let us take a channel problem. Let us say I have one standard cell row here one standard cell row here, and this is the routing problem. Let us say I want to connect a point 1 to a point 1 here, I want to connect a point 2 to a point 2 here. Similarly, there is a point 3 here, I want to connect it here, and there is a point let us say 4 here, I want to connect it here. So, this actually is similar to the problem which is shown on the slide. So, the connections have to be made like this, but in the real scenario, so how the wires will be laid out? They will be laid out in two metal layers in horizontal and vertical. I am showing you. Let us say one will be connected like this, this will be on one metal layer, this will be on the second metal layer, because all horizontal lines are typically on one metal, vertical line is on the other metal. This will be on one layer, this will be on one layer, this will be on the other layer. So, for connecting 3, it will be like this, it will be like this, it will be like this. For connecting 4, it will be like this, it will be like this, it will be like this. So, you see, if you try to compute the area of this layout, so how many columns are required in this layout? 1, 2, 3, 4, 5, 6, 7 and 8. 8 columns are required. And how many tracks? 1 and 2, 2 tracks. But what I am saying is that by moving these blocks around, I can also move these pins around. So, I can have a, by moving them around, so I can have a scenario where this pin 1 will be exactly above this pin 1, pin 2 will be exactly above this pin 2, this pin 3 will be here of course, but pin 4 will again be exactly above one above the other. Now, in this case how will be the layout, the wiring? This 1 and 1 can be connected directly on one metal layer, 2 and 2 can be connected directly, 4 and 4 can be connected directly, 3 can be connected like this. So, using this what will be the cost? Just if you similarly compute 1, 2, 3, 4, 5, 5 columns and only one track, one track. So, you can see even in this simple example, if I am allowed to move these pins around here and there, so I can minimize the area that is required for my interconnection, right. So, an integrated approach you can now think, where the various this floor planning, this pin assignment, you can merge them together. Even the placement and the routing that we will be considering later on, they can also be considered in an integrated way, so that you can have a holistic view of the whole problem. Like you can see, floor planning and pin assignment, if you consider them together, maybe you can get a better floor planning. Okay. So, you can get a better estimate of the wire lengths. There are a lot of related issues. So, this integrated approach basically talks about that. You can merge some of these steps, floor planning, placement can be merged, placement and routing can be merged, and so on. So, with this we come to the end of this lecture. Thank you.